Hey, physics, welcome to another flipped class lecture. Today we are getting into a new chapter. We're starting chapter 8 today, and we are looking at kind of complicated situations in which to interpret Newton's laws. So we begin a little bit early this week with some simple examples of how you can break complicated systems apart into different forces, and then we will introduce you to a new force that you have not yet met called the normal force. So it's totally normal. Get it? Yeah, anyway. Moving on. We're going to be talking today about how to analyze complicated systems and break them into simpler ones. So very often in physics you will not have simple situations where one object is moving at a given rate of speed and you have to analyze that. Most of the time it's a complicated system and various things are pushing on each other and pulling on each other, and there's lots of different things involved. And so you can't just look at one object and say that you've understood it. There is a strategy presented to you in your textbook that's very good, and it asks you in a complicated situation to break the complicated thing into its parts and analyze them all separately, and then try to put it back together and analyze the whole. So it asks you to break them apart into individual parts, and then to draw what is called a free body diagram for each individual part. And that allows you to analyze every one thing by itself. And then once you understand what they're all doing individually, you can understand what the whole is doing. Okay, so free body diagram is analyzing one part of a system and trying to get data from that to go back and reanalyze the whole. So this way you can break things down into easier to swallow pieces or easier to work pieces, okay? So here we have an example. If I were to want to analyze all the forces working in this semi-trailer as the truck drives down the road, I would have to look at what's happening in the wheel and what's happening, as the air resistance hits this thing, and what happens as the truck pulls on the trailer, and what happens as the trailer pulls on the axles back here, and the wheels turn, and the friction, and oh my, there's so much. Or I could look at it as a series of masses going down the road. I could try to simplify it a little bit easier. And so I have a series of masses here. This actually happens to have 3. Semi-trailer has 2, but you get the idea. We try to simplify the picture and look at just what we care about, okay? And then I might say, okay, I'm going to draw a free body diagram of just the semi-trailer. And it might look something like this, with the applied force of the semi pulling on it, the force of gravity, the friction as it gets resistance to its motion, and then the normal force, your new friend that you're going to meet later on today. Okay, so free body diagrams simplify things and helps you look at one part at a time. You could even do a free body diagram of R2-D2 flying through the air if you wanted to. You can do a free body diagram of anything. Alrighty, so those are free body diagrams. Now, oftentimes one thing acts on the other and it pulls or pushes it, and frequently it's not a direct contact force. It's not like I am currently pushing on my desk. Oftentimes it's something pulling on something else through the force that's applied through a rope or a string or a chain or a bar. And in those circumstances, we like to call them ideal strings. We don't want to worry about the physics of the connector. We just want to worry about the physics of the objects that are interacting. And so we would call a string an ideal string in physics. We can ignore its mass, we can ignore its friction, and we pretend that it doesn't stretch, and those kinds of things, just to make physics a little bit easier to work with. Similarly, if you pass an ideal string through a pulley and all you want to know is what happens at the other end of the pulley when you pull with a certain force over here, we can call the pulley an ideal pulley. We pretend it has no mass or friction or things of that nature too. And if we want to, we can ignore the presence of the pulley in the system and just look at the string. So there's lots of things that we can kind of do to simplify the picture of physics. One is to draw free body diagrams. The other is to do work assuming that strings and pulleys are ideal. So in this particular example, we have a mass, and we want to know with what force do I pull on this string to move the mass up. And I don't care what the mass of the string or the pulley is, I just want to know it's a 1 kilogram mass and how much do you pull. Okay, I can ignore everything else. Similarly, in this situation, I've got 2 strings, and now it matters that there's 2 points of attachment, and you'll get to pulley physics in a little while. But here again, I can ignore the mass of the string itself, and I can pretend that there's no friction in this wheel, and I can just look at this situation, or this situation, or this situation. And in all those cases, I don't add the mass of these pulleys, I don't add the mass of the longer string, I just know the weight and how many times it's going back and forth. Okay, so ideal pulleys and ideal strings help us to simplify the world a little bit. Now, I'd like to introduce you to your new friend, the normal force. It's totally normal that you don't know him yet, but he's going to be so common in your life from now on that you're just going to say, oh yeah, normal force. That's normal. What is a normal force? Is it just a force that you get to see all the time? A normal force is the force that resists gravity, that resists weight. Okay, and so I am putting a certain amount of weight on my chair right now, and the chair is resisting my weight with a normal force, meaning it's pushing back on me. It is the Newton's reaction pair force to the force of gravity. So the normal force of the chair is the reason I'm not falling through the ground right now. If gravity were the only thing working on me, I would be accelerating towards the center of the earth, and that would be a bad thing. So thankfully, there are normal forces which resist the force of gravity and the force of weight. Okay, so I'm putting a weight on my chair. The chair is pushing back on me with a normal force. My chair and I together are putting a force on the floor. The floor is resisting us both with a normal force, and you can see how this goes on and on and on to the foundation and the rocks underneath us. Okay, normal forces resist the force of gravity, resist the force of weight. It's always perpendicular to the surface that you're sitting on. So right now, because my chair is level and the floor is level, the normal force is the same magnitude as the force of my weight. But on an inclined plane, that's not true. Normal is always perpendicular to the surface, not necessarily straight up and down. Okay, and you'll see that in just a moment here. So this man leaning on a wall, he is putting some force on the wall, and the wall has a normal force back against him. Now notice that this is not up and down at all. This is actually horizontal. But you can have a normal force if there's a force against a surface. The surface resists that with a normal force. The man standing on the floor he's pushing on the floor because of his weight and gravity, and the floor is pushing back on him with a normal force. Okay, so normal always resists the pushing on a surface, usually because of weight and gravity. Here's another example. This box has weight on the floor, and the floor is pushing back up with a normal force. Okay, normal always resists the force of gravity or the force of weight, and it's always perpendicular to the surface. So if you have a horizontal surface that you're sitting on, then the normal force and weight are the same. But when that surface starts to tilt and you now have an inclined plane, now you're no longer dealing with a normal force that is of the same magnitude as weight or gravity, because your weight is now only pushing with a component of its vector straight down on the surface. Normal always pushes back straight up from the surface. So let's look at this real quick. If you have an inclined plane, you should choose a coordinate system where x, the x direction of the coordinate system, is in line with the plane. So you have a plane that goes this way. Now your coordinate system, this is x and this would be y. Okay, you'll see a picture of that in a moment. And then the normal force becomes positive in the y direction, right? Because it's always perpendicular to the surface. And so normal now is positive y. It's easier to work with. And the normal force is equal to just a component of the weight force. And we use cosine theta for this. And you'll see why in just a second here. Okay, so child sitting at the top of the slide. My normal force is directed upwards. Child is on a flat surface. Their weight goes down. Normal force is going up. Now, as a child slides down, their weight is still going down, but only a component of their force goes directly into the slide. And so the normal force coming perpendicular to the surface only has to overcome a portion of the child's weight. The other component of their weight is what's pushing them down the slide, right? And the normal force doesn't counteract that, otherwise the person would be floating in space. Okay, so normal always goes perpendicular to the surface, and when it's on an inclined plane, it's only part of the weight that it has to resist. So here's another example. On a flat surface, normal force and weight are the same. On an inclined plane, normal force always perpendicular to the surface, but it only has to counteract a component of the weight. Weight goes straight down. This is the part of the weight that the normal force has to counteract. And so here's your angle, here's your theta, And because it is the adjacent side of that triangle, we use cosine. So cosine theta times the weight gives me my normal force. Does that make sense? Here's a problem to give you some direct practice of that, okay? This woman who weighs 58 kilograms is running up a 17.2 degree incline. What is the normal force with which the trail pushes back on her? So here's a free body diagram. Her weight is 58 kilograms times the acceleration of gravity, right? And here's the normal force, and there's a difference between them of 17.2 degrees. So first we need to know the force of her weight. And so the force of her weight is her mass times the acceleration of gravity. So the force of her weight is 58 kilograms times 9.81 meters per second squared, gives us a force of 568.98 newtons. It's too many digits, but we're not going to round yet. You only round at the end, okay? So we're carrying this number now into our normal force equals the force of the weight times the cosine of theta. So the force of the weight we already determined was 568.98 newtons. We know that the incline, she's running up a 17.2 degree angle, okay? So 17.2 degrees. And we take the cosine of that and we get this number, which is very close to 1 because 17.2 degrees isn't all that much of an angle. And so 0.9552784, again, too many digits, but that's fine for right now. This is the cosine of theta. We multiply that times the weight force, and we get this number, 543.534282 newtons. Too many digits. Let's fix those digits, okay? Let's look back here. We have 2 significant digits. We have 3 significant digits. We have to go with 2. So 540 newtons is the normal force pushing back on her. That's the force that the trail exerts against the runner. Okay? If you have any questions, let me know in the comment section. One just quick other idea that we need to present to you, and that's the difference between measured and apparent weight. When we measure the weight of something, we assume that it is in a non-accelerating environment. When I step on a scale, I look down and see how much I weigh, and I don't do that while I'm in an elevator. I do that while I'm standing still, not accelerating. And so acceleration will affect the apparent weight of an object. So while something is unaccelerated, we can measure its weight exactly. If something is accelerated, then its weight changes. And let me show you a picture that will help you understand that. This little girl is taking her weight in an elevator that is not accelerating. Now it might be moving, but it's moving at a constant rate, or it's not moving at all. Okay? So we get an actual normal measured weight for her. But if the elevator is accelerating upward, not just if it's moving upward, but if it's actually accelerating upward, then we're going to get a greater than normal weight. And the reason for that is because her body is resisting the upward motion, and you can think of it as if she squeezes the scale a little bit more than normal while it's accelerating, okay? The elevator is having to change her momentum, and so it's the inertia of her body is pushing down on the scale more than just her weight. The opposite of that, if the elevator is accelerating downward, then her body's momentum is actually kind of moving upward a little bit, and the accelerator, or the scale, doesn't feel all of the mass of her body, all the force of her weight on the scale. So her weight goes down, less than normal weight. And should the worst possible thing happen and the elevator cable break, and she and the elevator are both in free fall, then once they have both reached free fall, then the scale can't weigh her at all. And this is the situation in space, right? In space, there is no experienced weight, even though you still are being accelerated by gravity. So you still do technically have weight. It's just that there's no way to measure that because you and the spaceship are both in the free fall of orbit. Okay? So actual weight versus apparent weight, or measured weight versus apparent weight. Let me know if you have any questions in the comment section below. and I will address those as soon as I can. I'll see you tomorrow in class. God bless you. Have a great evening.